This videotape deals with factoring. Let's start by reviewing the distributive law. A times B plus C is equal to AB plus AC. Used in this direction, like so, this is known as multiplying out. Used in the reverse direction, that is, starting with AB plus AC and putting it into this form, A times B plus C, this is known as factoring. And that is the topic of today's videotape. Let's start with a very simple example. 4x plus 8. We would like to factor. The idea is to think of this as AB plus AC. In other words, this is, say, 4 times x plus 4 times 2. We have now written it in the form AB plus AC. We can then factor out the a, or factor out the 4, and we will be left with x plus 2 in the parentheses. That is, 4x plus 8 is 4 times x plus 2 in parentheses. And we can check this by the distributive law. 4 times x, 4x, plus 4 times 2, 8. Okay, we were using it in the reverse order, the distributive law, so we could factor this expression. The idea is to try to see what factor the two terms have in common. Okay, we try to pull out the greatest common factor, the greatest factor that they have in common. And for the 4x and the 8, the greatest factor that they had in common was a 4. Let's try another example. X cubed plus x squared. We can rewrite this as x squared times x plus x squared times 1. We see that x squared is a factor of both of these terms. We can then pull the x squared out in front, and we would be left with x plus 1. In other words, we factor an x squared out of the first term, leaving us with the x. We factor the x squared out of the second term, leaves us with the 1. We can check this by multiplying out, using, once again, the distributive law. X squared times x gives us x cubed, plus x squared times 1 gives us x squared. You might notice that you could have said, well, x is a factor of both of these terms. Had you pulled out just an x, okay, you would have been left with x squared plus x in the parentheses, and it could have been factored further. Okay, so we try to pull out as much as we can. Factoring out is like dividing out. We are dividing this term by x squared, dividing this term by x squared, and seeing what we have left. Okay, let's try another example. 3x squared y minus 6xy squared. Once again, we are looking for the greatest factor that these two terms have in common. Okay, we notice this term has a 3 and this has a 6 in it. 3 divides this term and this term evenly, so therefore we can pull a 3 out in front. This term has an x squared, this has an x, so at least they both have an x in them. This has a y, this has a y squared. So we notice that both terms have at least a 3xy in them. Let's rewrite the first term as 3xy times x, and minus the second term we will write as 3xy times 2y. Okay, we can then pull the 3xy out in front, leaving us with x minus 2y. The first term and the second term each had a 3xy as a factor. That was the greatest common factor. 3xy times x would give you the first term, 3x squared y, and 3xy times the minus 2y gives you the minus 6xy squared for over here. We pull out the 3xy, we are left with the x minus 2y. Okay, let's try another example. 12 x cubed y squared z minus 20 x squared y cubed z squared minus 16 x y squared z cubed. Okay, we notice that, looking at the 12, the 20, and the 16, that for the constant factors of these terms, they have at least a 4 in common. Okay, 4 goes into 12, 20, and 16 evenly. Okay, so all these, and 4 is a factor for all of these terms, so we can pull a 4 out. The first term has an x cubed, the second an x squared, and the third just an x. So the most we could hope to pull out from all 3 terms is the x. Here we have a y squared, a y cubed, and a y squared. So we can pull out the y squared. We have a z squared, and a z cubed. We will then pull out a z from each term. What I'm going to do is rewrite each term, okay, as 4x y squared z times something. Okay, the first term, to go from 4 to 12, we'd need to multiply by 3. From x to x cubed, we need to multiply by x squared. From y squared to y squared, we multiply by 1. From z to z, we multiply by 1. So that is the first term, 12 x cubed y squared z, written as the common factor times something. Minus, now let's write this as 4x y squared z. Writing the second term as 4x y squared z times something. To go from 4 to 20, we would have to multiply by 5. From x to x squared, we'd have to multiply by x. From y squared to y cubed, we'd have to multiply by y. From z to z squared, we'd have to multiply by z. Multiplying this out, we would get 20x squared y cubed z squared, which is the second term, with a minus in front. Now the third term, I'll write that down here. Once again, I'm going to write it as the common factor, 4x y squared z. It has a minus in front because it's minus 16 there, times something. To go from 4 to 16, we'd have to multiply by 4. From x to x, we just multiply by 1. We don't have to write that. Y squared to y squared, once again multiplying by 1. Z to z cubed, we need a z squared. Checking this does give us minus 16x y squared z cubed, which is correct. We have now written each term as 4x y squared z, the common factor times something. We will now pull out 4x y squared z from each of these terms, leaving us with, from the first term, in each case we'll be left with a portion that is not underlined. We are left in the first term with 3x squared. In the second term, the minus 5xyz. And in the last term, the minus 4z squared. And we have factored the original example. 4x y squared z times, in parentheses, 3x squared minus 5xyz minus 4z squared. Now, in each example we've worked out so far, we have pulled out a common factor. This is the most basic type of factoring, and it's something that you should try to do whenever you have a factoring problem. Always look to see if there's possibly some factor that the terms have in common that you can pull out in front. Now, suppose you wanted to factor something like this: x squared plus 6x plus 8. Here, these terms have no factor in common other than 1. And we're not going to bother pulling out a 1. Okay? We do not mean pull out an x from these two terms and leave the 8 alone. We were looking for some common factor that occurred in all three terms, and there is no such factor in this particular example. Okay, what we're going to try to do, however, is to write this as the product of two binomials. A binomial is a polynomial with two terms. Okay, well, we're going to use what we know about multiplying binomials and reverse it to factor binomials. Let me just review how we multiply binomials. If we have x plus a times x plus b, we can use the FOIL method to multiply these binomials. That is, first we multiply the first terms for the f, then the outer terms, giving us bx, then the inner terms, ax, then the last terms, ab. And let me rewrite this as x squared plus, from these two middle terms, I'm going to factor out an x. I'm going to write this as a plus b times x plus ab. This is x squared plus ax plus bx plus ab. Okay, what I'm trying to do is to show you what we're starting with here. We are starting with a trinomial, polynomial with three terms, sort of like in this form, and we're trying to figure out what numbers go in here. We know that it's going to be an x and an x to start off the binomials. If anything is going to work, this will work, since the first term is going to be the x squared. Now look over here. We had x plus a times x plus b. The last term was the product of these two numbers, a, b. The coefficient of x was the sum. So what we're looking for are two numbers, say a and b, to put in here, which multiply to 8 and add to 6. Multiply to plus 8 and add to plus 6. Okay, and the answer in this case would be plus 4 and plus 2. Let's check this by the FOIL method. X squared plus 2x plus 4x for the plus 6x plus 8. Just like over here, we were looking for two numbers which multiply to the 8 and add to the 6. Multiply to the last number here and add to the coefficient of the x term. By the way, I just want to mention that this procedure is only valid if it's a trinomial with lead coefficient 1, or if it's 1x squared. I cannot use this kind of reasoning if it was 2x squared. This is based on 1x squared or just x squared. Let's try another example. X squared minus 7x plus 12. Once again, I'd like to factor this into the product of two binomials. We start with x and x, and I'm looking for two integers that multiply to plus 12 and add to minus 7. Okay, now, if two numbers multiply to plus 12, or to any positive number, either they're both positive or they're both negative. And clearly, what we're looking for here are the two that are both negative, since we want them to add to minus 7. Okay, now you look for numbers that multiply to 12. You can make 12 of 12 times 1, 6 times 2, 4 times 3. 4 and 3 seem to be the best choice, since if you put in the minus 4 and the minus 3 here, minus 4 and minus 3 multiply to plus 12, they add to the minus 7. Checking by FOIL, and you should always check your factoring by multiplying out x squared minus 3x minus 4x for the minus 7x plus 12. Okay, what about this problem? X cubed minus 4x squared minus 12x. The first thing that you might notice is that it's a little different than the ones that we had up before, because this one has a common factor for the three terms. Notice that all three terms have x as a factor. And any factoring problem that you start with, you should always look for a common factor. The two examples we just looked at did not have a common factor. You could not pull, say, an x out from all of those terms. Here, we are looking for a common factor other than 1. We notice that x occurs in each of these terms. We can pull an x out before we start, leaving us with x squared minus 4x minus 12. If you multiply this through, you get x cubed minus 4x squared minus 12x. We now have x times something which we hope to write as the product of two binomials. Following our procedure, we now have x squared. The lead coefficient is 1, so we can use our technique of saying we're looking for two numbers which multiply to minus 12 and add to minus 4. Okay, we want to multiply to minus 12 and add to minus 4. If you think about that for a moment, I'm sure you'll come up with minus 6 and plus 2 as the way to do it. Of course, you could have written x plus 2 here and x minus 6 there. Multiplication is commutative. The order of the factors is not important. Checking this, you get x squared plus 2x minus 6x. That's minus 4x minus 12. What about x squared plus 3x plus 6? We notice that these terms do not have any factor in common other than 1, so we don't start by pulling anything out. We would like, if possible, to try to write this as a product of two binomials. And we start saying, I'd like two numbers, two integers, which multiply to 6 and add to 3. Okay, now if you run through all the possibilities, in this particular example, you're going to see that you can't do it. I don't want you to feel that every trinomial is factorable into two binomials with integer coefficients. It's not. This is an example of one that cannot be factored, okay, any further than this. You cannot think of two integers that multiply to 6 and add to 3. 6 and 1, okay, 3 and 2, even with minus signs, you're not going to get them to add to 3. So this one does not go any further. Not further factorable. Okay, we could write over the integers here, meaning I can't break this down into the product of two binomials with integer coefficients. All right, how about x squared plus 6x plus 9? I'm looking for two numbers which multiply to plus 9, two integers which multiply to plus 9 and add to plus 6. If you think about that, you will see that 3 and 3 do it. They multiply 3 times 3, they multiply to 9, they add to 6. Checking by FOIL, you get x squared plus 3x for the plus 6x, 3 times 3 for the plus 9. Notice that in this particular case, the factors are identical. This is really x plus 3 squared. This is known as a perfect square, x squared plus 6x plus 9. Sometimes when you factor a trinomial, you get the binomial factor appearing twice, the same one. This is known then as a perfect square. Okay, let's try some more examples. How about x squared minus 10x minus 24? Looking for two numbers which multiply to minus 24 and add to minus 10. Okay, a lot of people looking at this right away think, oh, 4 and 6 multiply to 24, they add to 10, maybe that's it. Okay, but be careful. I want them to multiply to minus 24, which means they have to have opposite signs. They're going to add to minus 10, but when they have opposite signs, the addition is sort of like a subtraction, because you're adding sign numbers with opposite signs. Okay. The correct answer in this case, minus 12 and plus 2. If you check this out, you get x squared plus 2x minus 12x for the minus 10x minus 24, not x minus 4 times x minus 6. This gives you x squared minus 4x minus 6x, that's minus 10x. But when you multiply the minus 6 times the minus 4, that gives you plus 24. So you have to be careful. Everything is important. Whether it's a minus 24 or a plus 24, just changing the sign changes the entire answer. And always check your answers by FOIL. And then you'll pick up, for example, here that you have a plus 24 and you wanted the minus 24. Let's try another one. X squared plus 5x plus 6. This factors like so. We are looking for two numbers which multiply to 6 and add to 5. And of course, plus 3 and plus 2 will do it for you. Checking, we get x squared plus 2x plus 3x plus 5x plus 6. This is a fairly simple problem. The reason I'm doing it at this stage in the tape is I want to explain to you that if you can do this, then you can do all sorts of other factoring examples that you might not think you can do. A trinomial can be written in the letter y instead of in the letter x. In this particular case, the only difference would be that we would start the two binomials with y. Of course, it would be the same y plus 3, y plus 2 that we had there. Let's try this example. X squared plus 5xy plus 6y squared. Here we have a trinomial in both x and y. Once again, if you can do this one, you should be able to do this one. I'm looking for two numbers in this case which say multiply to 6y and add to 5y. Well, you're still going to start with the x and the x to get the x squared. And in here, you'll write 3y and 2y. Now let's check this by FOIL. X squared plus 2xy plus 3xy giving you the 5xy plus 6y squared when you multiply the last terms. One more example which is somewhat similar to this. X to the 4th plus 5x squared plus 6. Okay? It's not quite what we had over here, but it's similar in the sense that the middle term here is an x, and the first term is that quantity squared. Here, the middle term has an x squared. The first term is that squared. In other words, x squared squared giving you x to the 4th. And what we do is the same kind of thing, except we start with x squared and x squared in here. Okay? X squared plus 3 times x squared plus 2. Let's check this by FOIL. X squared times x squared gives us x to the 4th, 2x squared plus 3x squared for the 5x squared, and then plus 6 for the last terms. Okay, so go over this for a moment and look. We have here 4 different examples, all revolving around the same idea of looking for two numbers which multiply to 6 and add it to 5. X squared minus 25. A little different from the examples we've considered so far today because we don't have an x term. If that bothers you, you can think of it as x squared plus 0x minus 25, just for the moment. In that case, we are looking for two integers which multiply to minus 25 and add to 0. And of course, plus 5 and minus 5 work. If you multiply, we get x squared minus 5x plus 0x, or no x here, then minus 25 for the last term. Of course, most of the time when you're faced with a problem like this, you don't first put in the 0x. Rather, you think of this as the difference of two squares. Perhaps you have seen it in the form a squared minus b squared, written as a plus b times a minus b. Let's check this. A squared minus ab plus ab, that drops out, minus b squared. If you have the difference of two squares, you simply write it as one number plus the other and then times one number minus the other. Let's try some examples using this idea. Okay, y to the fourth minus 81. We have here the difference in two squares. If it helps you, think of this as y squared squared minus 9 squared. It's now in the form, say, a squared minus b squared. Okay, it now looks like a squared minus b squared. And we can write it as a plus b times a minus b. That is, we can write it as y squared plus 9 times y squared minus 9. The difference in two squares, difference of two squares, we write it as the sum of the two numbers times the difference in the two numbers. And we can check this by FOIL and get y to the fourth minus 81. Now, let's see if we can factor any further. The y squared plus 9 can't be factored any further. You'd have to have two numbers which multiplied to plus 9 and added to 0, and you couldn't do that. The sum of two squares cannot be factored any further, okay, over the integers here. Y squared minus 9, however, is really y squared minus 3 squared, and that can be thought of again as a difference of two squares. So y squared minus 9 can then be written as y plus 3 times y minus 3. How about x squared minus 16 y squared? This is really x squared minus 4y in parentheses squared. This is like, once again, a squared minus b squared. It can be written as a plus b, or x plus 4y times x minus 4y. Let's finish the tape with one more example. 3x to the fifth minus 48x. We want to factor this. At first glance, you might say, wait, this doesn't look like the difference in two squares. Okay, the first thing to remember with all factoring, I've been showing you rules, but in any factoring problem, the first thing to look for is to see if you have some common factor you can pull out. In this case, we can pull out a 3x from both terms, leaving us with an x to the fourth here minus 16 here. This multiplied out gives you 3x to the fifth minus 48x. We can then further factor the x to the fourth minus 16. This is difference of two squares. We can write it as x squared plus 4 times x squared minus 4. Okay, are we finished? Not quite. The x squared plus 4 is as far as we can go, but the x squared minus 4 is once again the difference of two squares. So we can write it as 3x times x squared plus 4 times x plus 2 times x minus 2, writing the difference of two squares as like a plus b times a minus b. And this brings us to the end of the example and the end of the videotape.